Hi, people. Thank you for joining. And for those of you seeing it in the streaming afterwards, thank you for watching. Today, we're going to do a little bit of a different talk. We're going to talk a little bit about games and how we can play them and how we can use computers to play them. So the talk title is Games Always Change. And a little bit about myself. I'm Liad. I'm the client architect at Duda. And the subtitle of this talk is Pixels and Robots, because we're going to divide this talk to two parts. The first part, we're going to see how to build a game ourselves in the browser with JavaScript. And the second part is how to make the game or teach the game to teach the computer to play the game for us. So the game will be smarter than us. So the first thing, the chapter 1 of our journey is the village of boredom. And why do I call it the village of boredom? Because you want to build a game, right? And in your head, you see the game and you think to yourself, okay, I'm going to build this game and I'm going to add a chat so every player can talk with each other. And I'm going to add like a video chat that all of my friends can talk to each other, and another video chat with the rest of my friends, and another box for one of my oldest friends. And then you start to say, okay, how do I develop a game in JavaScript? And you go online and you read about JavaScript game development, and you see like a 6 minutes read article. It's a good article, but it's only 6 minutes read. And you say, okay, how learn as you go, how do I build it? And you go to W3 schools and you see an HTML game example that just few boxes, and it kind of feels like that, right? How to draw an owl, just draw 2 circles and then draw the rest of the owl. So it doesn't really help. And then you go to the other end of the scale and you see these very long tutorials, hours and hours and hours on how to build a game, how to code a game in JavaScript. And you sit in front of your VS Code and you sit in front of your screen, your blank screen, and you kind of feel like that, right? You say, okay, I'm not going to do that. I'm not going to invest 30, 40, 50 hours of coding just to understand how to write a JavaScript game. So you get to the pit of despair, and the pit of despair leads you straight back to Netflix. But it doesn't have to be like that. So let's start with our chapter 2, Value of Pixels, and see what do we need to build a game in JavaScript. So the first thing, and obviously the most important thing, is the game graphics. And in JavaScript, the conference is about React, so you probably think to yourself, okay, I'm going to use React components to build a game. Well, it turns out that in JavaScript games, you don't really use React components. It's not that performant. You use an API that's called Canvas. And what does it mean? It means that you have in your head the drawing of how you want to build the game, how the map looks like, and how do you want the game to look, and how do you want the character to look, and you have this thing in your head. But what you really need is to draw a canvas in the body. And then you have an API for the canvas that allows you to draw on it as if you were the browser. So instead of putting DOM elements and animate them, you can just draw on the canvas. And you get it you do it by getting the context, and then just using this context. And the Canvas API is very rich and it's very easy to search to actually draw your game graphics. And then you have to put your game elements. So since you don't use React and you don't use state management, you just put elements, you just put objects on your in your code. And for example, you have the first player and you have its coordinates and is it running or not, is it healthy or not. And then you have the enemy. For some reason, it's John McClane, but Fry fighting John McClane, and you have its coordinates and the velocity, and these are the things that represent your elements. And then the canvas you will use the canvas to draw from these objects. You have to listen for controls, right? So you have the keys, and then you listen to event listeners on the window, key down or key up. And once you listen to those events, you register the key. You say, okay, if the key was pressed, then I put it as true. If the key was lifted, then I put it as false. And this is the code that does that, right? You say keys.left. If the key code is left, then you put keys.left is pressed, and etc. And then you have in the keys object, you have the list of all the keys that are pressed. Then you have to implement the game logic. So the game logic is actually where the game takes place. So for example, you say, okay, if the keys.left was pressed, then I will increase the Batman velocity X. If it's down, I'll increase the Batman velocity Y. And then you have to say, okay, to detect for edges, if the Batman.y bigger than the screen height, then I have to put it in the screen height. And then you say, okay, if Batman and Superman are the same X, then you reduce Batman's lives. Otherwise, if it takes a heart, you increase its lives. And if it's Martha, you break. And all this is to, you have to make sure that the code follows the logic of the game that you want to do. Now, bear in mind, all of those things are happening in one frame of the game. So that brings us to the game loop. You have to run a loop using request animation frame, and you have to put all the magic of the game inside the loop. And every animation frame, you run all the logic of the game. So you basically update everything according to the keys that were pressed, like we saw. And then you run the actual game logic. You detect collisions, you detect edges, everything. And then in the end, when you have the updated objects, you draw them on canvas. And then you run the next frame, and the next frame, and the next frame. Now, we talked about drawing on canvas, but it's not that easy. You can see here, for example, how to draw this pixel art character on the canvas. And you see that it's very, 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 very long to do it in code. We usually will use sprites. Sprites are, as you can see here, you have all the modes of the character in one image, compressed into one image. So you can just use the part of the image that you want according to the position and the velocity of the character. And when you see all that, do you still want to build a game? Do you still think it's easy? Probably not so much. Luckily, we have game engines. And game engines are frameworks that encapsulate most of the things that we don't need to worry about, and they just let us focus on the graphics and the logic. That brings us to chapter 3, or the middle of efficiency. So there are a lot of JavaScript game engines. Phaser is one of the best ones, and you have Pixie.js, which is also very good. You have gdevelop. And most of them require some sort of learning or previous knowledge in order to use them. I chose to show here a framework that's called bitmellow.com. So bitmellow is a very simple, very easy JavaScript game framework. And the nicest thing about it is that it lets you export your logic, export your HTML, export your assets, and use it in your own application. So let's see. When we go inside bitmellow, we see this kind of screen. You can see here on the left, we have the tile editor. So the tile editor basically lets us edit the tiles that are going to are going to be used for in the game by us. So we can edit the actor. We can draw here like something else if we want. If we want to add another character, we'll see later in the talk how we're going to implement this. And you have the tile map editor, and that basically it helps you edit the actual game, the actual map of the game. You have a sound editor, which is very nice. You can add sounds to the game. And the most important part is the code. Don't worry if it's too small here. We're going to go over it later in greater details. And you can export your projects, which is nice. In the tile editor, you can see here on the right some tutorials. So if you want to plan animations, you can see here how to plan the animation. If you want to draw clouds, you have here some explanations, what is best, how it's the best way to draw the cloud, how they should flow. And that's why I really like bitmellow. Okay, so bitmellow is exporting an HTML, and HTML is not something that we can use. It's exporting a single HTML that basically includes all the data of the game, and we don't want to use that. And for that, for those of you who wondered how everything is, how any of that is connected to React, so we'll use npx create React app to the game, and that's the first and the last appearance of React in this talk. So we're going to use a game. We use the create React app, and we're going to build ourselves like a small React app, and we're going to break the HTML into the parts. So we're going to import the bitmellow engine. We're going to take all the game logic that we wrote and put it in game.js, and we're going to import from the project data.json. And in the React, in the game wrapper, we're just going to init the game logic. This is the JSON, and the nice thing about BitMelo is that it lets you export only the JSON, so you can keep editing in BitMelo and exporting and overriding only the JSON. Okay, so let's see what we have. So we have here this cute game. So you can easily write a game like that, where you just go and collect mushrooms, and you can animate the text, and you can decide which mushroom appears where, and you can see here the text that tells you how many mushrooms you've collected. And basically what it does is that you can see that engine on update, that's the loop that we discussed. So it draws the map and then draws the targets. So for each target, for each mushroom, if the target wasn't grabbed already, it draws the tile, and it's really easy, just screen.draw tile, that's all we need. And then it updates the player. So what does it mean to update the player? So it just you're just taking the coordinates of the player, you check for keys like we saw, and just a second, check for keys if we saw, and then you update the coordinates, and then you calculate the distance to the target. And if the distance is small enough, you say, okay, the target was grabbed. And the last thing is just drawing the player. And you have, like you saw in the tiles, you have 3 tiles for the player, because it can go when it walks, it lifts one leg and then lifts the other leg. So you say, okay, you count the frames since it started walking, and then you decide which tile to draw. So it's really nice. Yeah, so it's safe to say that we leveled up, and now we can easily build games using the BitMelo engine. And now it's time to do something a little bit more interesting. It's time to visit the Mountain of Wisdom. And what does it mean, the Mountain of Wisdom? Well, building our own game wasn't the end goal for us, right? We wanted to make the computer play it. And the idea is that in the last years that you can see a lot of papers, a lot of works about AI playing games. And you can see here StarCraft by DeepMind, that's something from the last years. And it's not as complicated as it seems, but it requires a lot of training. And we'll see in a second how does it work behind the scenes. So you can see here an AI playing Super Mario, and you can see here what happens behind the scenes. So you can see what happens behind the scenes, where the AI looks at all of the parameters and then decides what to do, what kind of action to do. Okay, so the thing about using AI instead of coding the rules is that if you want to play a game by coding the rules, you have to tell you have to code and to tell the computer what to do in every step, in every state. Meaning, if the player.x larger than enemy.x and the player has enough health, then move towards the enemy, otherwise run from the enemy. And if the y, then do the opposite. And when you use AI, you just try to infer the rules from the data. So you tell the computer, okay, this is the input, this is the result, this is the input, this is the result, this is the input, this is the result. Just train on that, and then I'll give you a new input, and you will tell me what's the new result. The thing is that with computer games, we don't have all the inputs, and we don't have all the results in advance. So, for example, in StarCraft, we can't say, okay, in this frame do that, in this frame do that, in this frame do that, because we don't know that. So we have reinforcement learning. Reinforcement learning, meaning that we teach the model, we teach the computer to learn from rewards and punishments instead of results, instead of labeling the data. What does it mean? Let's say we have an agent and we have the environment. So the agent wants to play the environment. So first of all, our agent needs to observe the state. And the state usually means what happens right now. How can I quantify what I see right now in the game? For example, for Super Mario, it can be the horizontal, the vertical axis, and how many enemies do you see, how many lives, how many coins, for example. That can be the state. And the agent observes the state, it runs some sort of processing, and then it invokes an action. and it sends the action to the environment. And it doesn't know anything about the environment. It just knows that it needs to send the action there. So the environment gets the action, and in return, it returns a reward. And the reward can be 0 if nothing happens, and it can be positive and can be negative. It depends on the outcomes of the action. And the environment also changes the state. So it sets a new state. So now the question is, how good is every action? So when an agent sees a state, it needs to know how good, it needs to look at all the actions and select the best one. So how do you measure the best one? How good is the action? Well, you calculate the immediate reward that you get from the action. And since it brings you to a new state, you also calculate the expected reward from this new state. So if it brings me to a better state, this action is better than some action that brings me to a worse state. So basically, we just hold some sort of a table. And in this table, for every state, for example, now we're in state 2, we look at the actions and we see that the best one here is up, right? Because it has a value of 11. So we select up. And now if we select up, we get some sort of reward, let's say 2. And then it moves us to another state, because we were in state 2 and then we selected up. So now we're in state 3. In state 3, we select the best action here, which is right. But we also update the value of the up action from the previous state, because now we know it gets us to a state where where the value is 10. So now I update it. So basically, reinforcement learning is just try and fail and try and get reward and try and fail and try and get reward and try to learn how good are the actions when you do that. Okay, and here's an example of a Flappy Bird, something that tries to play Flappy Bird, if you know. And basically, that's what it does, right? It saves in the table the state and whether to flap or to do nothing. And it takes a lot of iteration. It takes something like 25 minutes until it learns to play it completely. And if you have a very complex state where you can't put it in a table, you just put a neural network, and that's a whole bigger world to discuss, a neural network that gets the state and then outputs the action. That's what we are going to use. For more complex games, you don't even use a state, you just feed the frames. You just say, okay, this is the frame of the game, just decide what to do. This is the frame, this is the actual pixels, not the state. That's what autonomous cars are doing. Okay, everything is cool, but how do we implement it? So we have a nice framework that's called TensorFlow, which can help us. And we have TensorFlow.js, of course, that allows us to use those sort of machine learning in JavaScript. And it can do really cool things. I recommend checking awesome TensorFlow.js and also the Metacar project, which is not using TensorFlow, but it's autonomous vehicles in the browser, which is cool. And we have OpenAI, which gives us a gym, an environment for retro games. So we can just send actions, get rewards, send actions, get reward, and then train on how to play those games, which is kind of nice. We can just write code that plays this game. Okay, but we're going to use something that's called Reinforce.js. And Reinforce.js by Andre Karpati, it's really easy to use. You just define the name of the states that you expect and the name of the actions that you want. And then you initialize an agent. You act on the state. You tell the agent, act on the state. And then the agent returns to you the action that you need to do. You try to execute the action in the environment, get the reward, and then you tell the agent to learn from the reward. And it's that easy. That's it. I mean, you just initialize the agent, you act on a state, you get the reward, you learn from the reward, and then in a loop, you do it all over again. So that's what we're going to use. We're going to use change game.js to expose our actors, the actor and the target, and to allow us to fire action. And we have here the AI.js code. I'll share the code later, but basically it's really easy. It basically tells you, it says, okay, get the actor and the target, get the distance between them, act on their coordinates, invoke the actions, invoke the action, get their new coordinates, and then get the reward. And the reward is, did you get closer to the target? Then we'll get positive reward. If you got further from the target, we get negative reward. And we learn from this reward. So now we can just start give the computer to play for us. So you can see here the rewards on the left, and you can see our agent playing, and it's exploring, and it gets positive reward if it gets closer to the mushroom, and it gets negative reward if it gets further from the mushroom. And you can see that it got a little bit stuck, but quickly it gets to the mushroom, and it learns to get closer to the mushrooms. And that's a computer playing, yeah, that's the AI playing, and it's learning and learning. And you can see that the rewards are negative because every time it takes a mushrooms or a cake, it gets further from the next one. So the cumulative reward are negative. And since everything is saved, modeled in a network, we can actually save this model and then load it. So if I load the model, I load like a previously trained model, my agent should be better. My agent should be, it should use all the knowledge that it already learned in previous iterations in order to play. And you can, I'll share this this website later, and you can just play it, and you can see that when it gets to 30, 40, 50, it gets really, really good. So cool. Now we have AI, which is very good. And now we can start a little bit to explore with that. I think we deserve a level up for that. Okay, so now we get to the final chapter, the river of opportunities. And since we have AI, and the AI is not connected at all to the game, we can just add other tiles, add different game logic, and the AI will still be able to play this game. So let's say I draw a lot of other tiles now. I draw Rick and Morty, and I draw some stars, and I want my game to be in space. So I put my game in space. I don't change at all the AI code, and I just start. And I let my Rick try to collect planets. So you can see it collect the planets. And I loaded the previously trained model from the mushroom game, but it doesn't matter because all I changed was the graphics and some of the logic of the planets. And you can see that Rick is still a little bit confused, but it won't take long until it takes Mars as well, and then the cake. So that's really nice. And if you let it run, it gets really, really good. We can also add another player and change the reward. So instead of rewarding for getting closer to something, we can reward for getting further from something. So let's say we have Rick and Morty, and we have Morty running around here, and we will input Rick's coordinates and Morty coordinates, and we'll change the reward. So instead of rewarding for getting closer, we'll reward for getting further. So we'll add a minus here, and then we can see that Rick's trying to escape Morty, and I can't load anything here because the model that I trained earlier was about getting closer. So now we need to let Rick learn it on its own to get further from Morty. And you can see that whenever Morty gets closer, Rick gets further away, and eventually it gets really, really good at that, and the rewards are getting higher and higher. Well, I think Morty is picking Rick here, so he puts it in the corner. Okay, and the last thing that we can do is try to add the reward. So add the reward for getting closer to something and a reward for getting further from Morty. And let's see how it works. So you see the reward here is -1 for getting closer to Morty and +1 getting closer to the target. And here Rick gets a little bit more confused because it needs to move in the space in that kind of way. For example, in this situation where Morty is very close to the target, it doesn't know what to do. And you can see in the rewards are getting negative very fast. But again, if you let it run for a few minutes, it gets really, really good at that. So what did we have? We have the village of boredom, which led us to the pit of despair. And then we had the valley of pixels, where we learned how to build games, the meadow of efficiency, the mountain of wisdom, where we learned how to add AI to the games, and then the river of opportunities, where we saw that once we have this model, we can do anything with it. So don't let your dreams be dreams. Just do it. Just do it. If you think about something, just read about it and try to implement it. And that's it. You're awesome. I was Liad. Here you can see I have the Git repository and the website to play with, and I'll share the presentation. And thank you very much.